Definitions, let's just talk about balance point here a little more. It's the lowest outdoor temperature for which the output of the heat pump can heat the house by using the compressor only. Below this temperature, the strip heat might be needed to come on. So this is create, a heat pump balance point chart. The first thing that you do is you create the heat loss of this house. You need, 1 point to do that. You can take your heat loss at any given outdoor temperature. Usually it's your design temperature, and you anchor it over to 65 degrees. Sure enough, the warmer it is, the less the house needs for this to maintain temperature. So yeah, this house has a 45,000 BTUs at 9 degrees. Our first one here is a 2-ton, and if we just draw a straight line between the 17 and 47 degree AHRI rating points, you get a nice straight line. So the balance point where the two lines cross is 37. Not really a very good fit. The 3-ton gives you 33. We're getting closer. The 3-ton would give you 28. Nice fit. I think that'd be a very nice fit for this house. 4-ton, you're getting down to 25. And boy, you're probably paying lots for that, and chances are you'd probably also have to increase the size of the ductwork to handle that. Another way of looking at it, if you're going to use a 30-degree balance point, is what's the heat loss at 30 degrees? It turns out 30 degrees in Portland, Oregon is exactly the same temperature as 30 degrees in Bend, Oregon. So one thing you could do is you could just go into your software program and say, I'm going to override the design temperature. I'm just going to call it 30 degrees. That way you could just say it's 30 degrees, and I'm going to go into the detailed capacity tables and just see what their output is at 30 degrees. We see that the 5-ton gives you almost 40K. The heat loss is around 30K, so we could say that's oversized. The 4-ton gives you a nice fit. The 3-ton hits it perfectly. The 3.5-ton hits it perfectly. The 3-ton starts to fall short, 2.5, 2, and then just a little bit ridiculous, the 1.5 tons. So this is one way to think of balance point. You're just basically seeing what the heat loss is at 30 degrees, and then double checking what the capacity of the equipment is at 30 degrees and trying to get as close to each other as possible. So sometimes we hear, hey, how come you make such a big thing about the 30-degree balance point? Does it really make that big a difference? We look at Boise, and Boise is pretty similar to Bend, Oregon, for instance. And what we're looking at here is a bin temperature chart. These are how many hours every year that the temperature is in a certain bin. So between 40 and 44 degrees in Boise, we have 848 hours a year. So if you drop the balance point between 40 all the way down to 30, that's 1,553 hours, or the equivalency of 65 days that strip heat would have to come on to help heat the house. And boy, that's a lot of electricity to do. Let's take a look at Seattle. It's obviously more mild, but even in the mild Seattle, there's 930 hours between 30 and 40 degree F. That's equivalent to 39 days. So even in mild climates, getting a balance point of 30 is critical to energy savings and client satisfaction. Northwest heat pump sizing, we really get a break here. In humid summer climates and climates where cooling usage is high, Manual S dictates that the heat pump size not be more than 125% of the cooling load. The good news, when we get hot, we get dry. Manual J and Manual S, as they should be, are quite concerned about dehumidification in humid climates. When we get hot, we're not a humid climate. So if we stuck to this 125% advice we get out of Manual S, we'd often end up with tiny heat pumps that use lots of electricity. In most parts of the Northwest, 80% to 100%, maybe on the coast of heat pumps energy is used to heat and not cool. So we're much more concerned about the efficiency in heating than we are in cooling. If you really want to dig into Manual S, the 1995 version says that if you live in a heating-dominated climate with dry summers, which is most of the Northwest, you get to use economic considerations, and that's really what the balance point of 30 degree does for us. Sort of gives us the best economics possible. Please notice that on the cooling design temperatures, they give you a few options. The 2%, that would be only 2% of the time does it get above 83 degrees. The 1% is 86. The 0.4 is 90. Well, summers are getting warmer and summers are getting smokier. The mean extreme is 99. I think that you would be fine, quite honestly, in climates such as Portland, Oregon, where there is a big gap between the average summer temperature and our mean extreme. I think you'd be fine using this 0.4 at 90, or maybe in some cases the mean extreme. But I would never use these 2% or 1%. Heating, you can go for the 99 or the 99.6. It's the difference of 5 degrees. I would not use the mean extreme for the heating in Portland, Oregon. This is the official summer climate map of America. You know, down in the southeast, if you're flowing down to Baton Rouge in the summertime, you probably walked off the airplane and immediately started sweating and could not wait till you hit your air-conditioned hotel room. It's really hot and it's really humid, and that humidity is the reason we call it air conditioning and not air cooling. Down in muggy places of our country, it is just as important to dehumidify the air as it is to cool. Air conditioners down in this part of the country have to be sized for both latent load, which is the ability to remove moisture from the airstream, and sensible load, which is the ability to cool the air down. Back in the Northeast, it's not quite so hot, but it can still be really humid back there. Our Southwest is just blazing really hot, but it can be dry as a bone. In the Rocky Mountain states, hot and really dry. And up here, we're sometimes hot, and when we do get hot, we get dry. So yeah, just going over the definitions of sensible and cooling load. The sensible is that part of the cooling load that involves lowering the dry bulb temperature. And dry bulb, this means a regular thermometer. If you put it in your house or you put it upside, that's the dry bulb temperature that you're getting. The latent load, that's the part of the cooling load that involves removing water vapor from the airstream. And in muggy climates, this is critical. Before sort of Manual J and Manual S came out with such good guidance, we had contractors in hot, humid climates with customer complaints, and they'd simply put a bigger air conditioner in. The trouble with that is, yes, it cooled down the house, but rather than being hot and sweaty, you ended up cold and clammy, a condition that nobody likes. When you have a latent load, it reduces the ability of the air conditioner to lower the air temperature. Some psychrometric definitions. Dry bulb, that's the dry bulb temperature measured by an ordinary thermometer or thermostat. Wet bulb. Obviously, you have digital psychrometers these days. This is an old school way. I like these ones because I can understand them. You have a dry bulb, and then you have a wet bulb on this mercury thermostat. It's a cotton sock, and by the way, it has to be cotton, and a little water reservoir down here. So the cotton sock wicks up the water, and then you hold the main body and you walk around the room and you twirl this for a while. If it's really dry, you get a lot of evaporation off the cotton sock, which lowers the temperature of that mercury. If it's really muggy, you don't get so much evaporation. So when it's dry, you get a big difference between the dry bulb and the wet bulb. And when it's muggy, you don't get much difference at all. So all of us have probably heard that, hey, that air conditioner is getting us a 20-degree split. It's working just fine. And, you know, for large parts of the year in the Northwest climate, that's true. Say we have an indoor dry bulb going into the coil, the indoor coil at 76, and the indoor wet bulb is 62. Yep, guess what? You have the ideal temperature split. But this is how you get out there. And it's early in the day, the system hasn't been running to dry out the air. It's a little muggy. Let's just say you got a 68-degree wet bulb, which is which is pretty wet, and the same 70, let's say a 78. Well, then your expected temperature drop across the coil will be 17. Let's say you had a 72 degrees indoor dry bulb temperature, then you'd only be expecting a temperature drop of 14. So while the 20 degrees generally works for us in the Northwest, it's still nice to know something about the psychrometric conditions you're testing under. What Manual S says about cooling, don't oversize by more than 115%. That's hard, no more than 125% if it's a heat pump. Why are they so worried about this? Is because they're worried about dehumidification. The good news is that we don't have to worry about dehumidification in the summertime in the Northwest. If that air conditioner is running at all because it's hot, it will provide sufficient levels of dehumidification. Also, older air conditioners had a big penalty for not having long cycles. Newer equipment has improved significantly. What the penalty for cycling is something called the C sub D, or the coefficient of degradation. It's used to describe how the efficiency of air conditioner heat pump is degraded by cycling. It used to be C sub Ds would hit you up with maybe, a 25 or 30% penalty if it's cycled. The new ones are much lower than that. A good estimate that oversizing an air conditioner in the summer by a ton might only get you a penalty of 40 degrees on energy efficiency. I'm not advocating oversizing. Again, just hit this up. Manual S says don't oversize. Why? Because they are quite concerned about dehumidification. Sizing for air conditioners. Every manufacturer presents their detailed capacity just a little bit different than every other manufacturer, making our lives sort of complicated. But regardless, the process is usually the same. You find the outdoor design temperature. In this case, it's up here near the top. You determine your CFM, and this happens to be for a 2-ton system. You start at 800, you go to 900, you go to 1,000. Please notice it doesn't go down to 700 or 600. So again, these charts are only valid that if you have perfect airflow and perfect charge. You pick the lowest entering wet bulb, 62 or 57 degrees is safe. Remember, it's going to be hot. The air conditioner is going to be running for a long time, and the air will get dried out the longer that air conditioner runs out. And then you locate the sensible capacity. And this manufacturer showed basically sensible capacity in a different table. So please notice here at 72 degrees entering wet bulb, the sensible capacity is only 13,000 BTUs per hour. The total capacity is 26,000 BTUs per hour. The difference is all tied up in latent capacity, in removing and turning that humid, muggy air in form of vapor into water. Boy, at a 62 degree entering wet bulb, it's almost identical. By the time you get down to 57, it is identical, meaning the capacity of that machine is all sensible and it's available to lower the temperature of the air as it goes through the coil. This is another way of looking at it. Again, we're going to find outside temperature. Here, the axis is here. This is, say we're going to pick on 95 degrees today. Determine your CFM. Notice that they don't give you any CFM. It tells you it's fixed at 1200. You fix the lowest entering wet bulb. We're going to use 59 degrees. Locate the sensible capacity. Well, here they give you the total, which is 32, and they give you the sensible capacity, which is 29. So this is a 3-ton machine. And they're telling you that underneath these conditions, the sensible capacity is 30,000 BTUs. It's not 36,000 BTUs. And if for whatever reason you wanted to go to a humid climate, say it's all the way up to 67, your sensible capacity would be actually less than a 2-ton machine, roughly at 21,000 BTUs. A little word about geothermal. At least one person in your company needs to be ICSPA certified. We'd like to see a balance point of 25 degrees or lower. And here's the important part, is when you're doing the calculations, the balance point must be calculated in incoming water temperature of 30 and not 50. There's a reason we put antifreeze in the loop, because it does get cold and might freeze. And by the end of winter, In most systems we've inspected, the incoming water is close to freezing, not below freezing. Manual S, when it comes to selecting these things, understand that late and sensible cooling loads are two separate items, and you have to meet each to obtain comfort. In cooling mode, the good news is our latent load is really tiny. Just to show you just how this works, infiltration accounts for most of the latent loads. In humid climates, leaky homes let that moisture in. In dry climates, it's so dry outside that the leaky homes tend to have lower latent loads. Sizing for cooling, most parts of the West, it's easy to handle the dehumidification. Air conditioning, originally meant two things, dehumidification and lowering the sensible temperature. Other key part is how much insulation is in that house. What are the windows like? What are the ducts like? Those are the critical elements. And, I'm old enough to know that, old enough to remember that when we used to do this, we had big 3-ring binders that we got every year. And we had to, carefully look up the new equipment output tables and looked at carefully. Now everything is online. But basically the process here is, do accurate heat loss, heat gain. One thing I would like to stress here is that a lot of programs for their default window U values, especially in the Northwest, we have a long history of codes requiring U values for windows of 0.4 or less. And some programs, if you say you have a double pane vinyl window, they'll assume a U value of 0.5 and a fairly high solar heat gain coefficient. In the Northwest, almost all our vinyl windows are 0.40 or better. Any new home will have a 0.35 or better. So double check the default U values of whatever computer program you may be using. This is what the detail stuff. Insulation, none, some, fair amount, or a heck of a lot is usually sort of close enough. House tightness, this is another error we see a lot. ACH, the leakage rate of the house, air changes per hour, is usually between 0.35 and 0.8. It's never 2. I have seen heat loss and heat gain calculations at 2. That's a barn with the door open on a windy day. Window solar heat gain coefficient is critical. You can usually find that generally in the Northwest. It marches right along with the U value. So if you have a 0.35 U value window, chances are solar heat gain coefficient is very similar. Orientation is critical. Windows that face east and west get most of the summer sun. It's low in the sky and it can just beat through it. So make sure you have the windows in the house pointed the right direction. Duct multiplier is critical. 15 to 20% is really a pretty good estimate. I know many of you don't do duct leakage tests, and that's perfectly okay, but I urge you to do what I at least call the Homer-Simpson duct leakage test. That's where you turn the system on, let it run for a while, so you're either heating or cooling, and go around to each register. And is there conditioned air coming out of each register? If not, go find out why. It might be a disconnect or it could be a closed damper. House size is important, but not as important as insulation levels and window U values and window orientation. You need to know the capacity of the heat pump at your desired balance point. You can either do that by direct lookup or drawing the traditional balance point diagram. And also, don't forget to pick the right location. Remember where you live.